Hello, in this video I'll be solving the question of implementing this finite state machine diagram using VHDL code. First we'll try to read the diagram and try to interpret it to figure out what input ports are needed, what output ports are needed, and the state names before we start the implementation. So from the diagram we can see that we have an input that changes between, or that can have a value of 0 or 1. Therefore, it is sufficient for the input to have one single bit. I'm going to assume that the input is named X, and X is a 1-bit port. The bottom half of the states, which is the circles, the bottom half of the state shows you the output. We have clearly one output, but this output value changes depending on the state we're in. For state 0, the output value is 0. When we move to state 1, the output becomes 2, or it will have the value of 2, and so on. So the output changes between 0, 2, 4, 6, and finally 8 in state 4. So to represent 8, which is the highest value we have, we will need to write it using binary as 1, 0, 0, 0. This indicates that we will need a minimum of 4 bits, or 4 bits are sufficient to represent the output. So I'm going to say that the output, let's say it's called y, and y is a vector containing 4 bits. For this particular example, I can also make the output an integer of data type integer, but this means I'm using 32 bits just for y, and I only need 4 bits to begin with. You can also see in the question there's a hint saying use a 4-bit vector for the output. So now we will list all the state names based on the diagram. I have S0. The state name is what appears at the top of the circles. So I have state 0, state 1, state 2, state 3, and finally S4. This is the state name S0, S1, S2, up to S4. This name can be anything else. It could be, let's say, state start, for example. But it's always going to be based on the diagram. Whatever the diagram says, we will have to implement it accordingly. Next, we will, optionally, we can fill a table to show each state and what its output is going to be. And based on the input, the current input, which we named X, what will the next state be? So our input is called X, the output of the state is called Y, and Y is going to be a vector, so we can convert the value to a 4-bit vector. So 2, which is the output of S1, can be written as 0, 0, 1, 0, and so on. I'll explain just the first part of the table, the rest will just follow. So first, the current state S0. When the current state is S0, we can look at S0 and see where the arrow takes us if the input received is 0. So from S0, we receive an input value of 0. That means the next state should be S1. So we'll fill the table accordingly. Now we'll look at S1, but when the input received is 1. Sorry, S0, when the input received is 1. We are in state 0. We receive a 1. The arrow labeled 1 goes or points towards S3, so we'll fill the table with S3, and so on. The rest of the table can be filled accordingly to help with the coding part. Now we can go to Quartus. We can create a new folder in the desktop, let's say, and call it lab 4, for example. So I already have a folder created. I will create a folder within this folder. I will create a project within this folder. I'm going to call it lab 4 or FSM, for example. I'll call it lab 4, then I will click finish. Now before starting the implementation, I can find a template or sample code that uses FSM just to help me get started. I will use a template from the lab sheet, and then I will create a new VHDL file. Click new, choose VHDL, and then click OK. Now, this is already FSM and it's used for the previous question. I'm going to call this one FSM2. Remember to update the name here as well in the architecture part. And then we'll try to save the file, save as or file save, and then call it the same name as the entity, which is FSM2. You can check here that there is a file named FSM2. We will make this file top level entity before compiling later. Or we can do it right now. Now we can see the design plan we made earlier and then start modifying the code accordingly. So here, our input is named X. So I'm going to add X as an input. Since X is 1 bit, I can list it next to the clock. If it's a vector or let's say an integer, I will have to list it separately. Let me list it separately just to help you, use this code, to allow this code to be modified accordingly, so, as needed. This design does not have a reset. I can tell from here or from the question description. The question says there is no reset, so I can remove the reset input from the ports. And again, you can list the next input X here, since it's also of type N, standard logic. I'm going to add X separately. This way, in case I need to change the data type, that will be possible as well. So X is also input, and it's 1 bit, so it's standard logic, semicolon, because I have more ports to list. I have an output named Y. It's not called output anymore. And this Y is a 4-bit vector. So this is the data type for the output. If it's 1 bit, you can say standard logic. If it's an integer, you can say standard logic. It's a vector of 4 bits, so we'll write 3 down to 0. Now, we need to list all the states. If I don't have S0, S3, I will have to remove them all. But now my design happens to use the same state names, so I'll keep them as they are, but I'm going to add one more state, which is S4. This line is still needed. The states the state variables or signals. So I'm going to keep them as they are. Now, when it comes to the process, the sequential process, there's no reset. So I'm going to have to remove the reset from here. And I cannot check reset if it doesn't exist. So I'm going to have to remove it from the condition here as well. Whenever you remove an if statement part, of course, you'll have to remove what you want to do if that condition is met. So I'm going to start removing everything from here up to here. This way, my process will only check if it's a rising edge and then move to the next state. The else part is not really being used. I can either leave it or remove it completely. Now, since my design has an input, for the combinational parts of the code, besides the current state, I need to include the input, which is X in this case, input X. Now I'm done with this part of the code, of the design. Now, the part responsible for updating the next state depends also on the input, based on the state diagram that we see or the state table that we came up with or extracted earlier. So when you are in state 0, the next state is not always S1. It depends on the input X. So if X is 0, the next state should be S1. Else, if the input is 1, we want to move to S3. So for this part, we will need to output Y, which is 0, 0, 0. So Y is 0, 0, 0, 4 zeros, when we are in state 0. So I can still keep the vector notation. So I'm going to say Y equals 0. But I cannot decide on the next state yet. I have to check the input first. So I'm going to add an if statement. If you don't remember the syntax, you can always go up and find an example of an if statement. If the input X is 0, since it's 1 bit, I'm going to use single quote. If the input X is 0, then I want my next state to be S1. else, I'm assuming if x is not 0, it's going to be 1. So else, the next state will be based on the state table we have here. Else, the next state, if the input is 1, is going to be S3. So again, when the current state is S0, we output y equals the vector 0. And then we check x. Based on x, we decide on the next state, whether it's S1 or S3 or any state depending on the state diagram. And this part of the code, so I'm not done yet. I need to end the if statement using this syntax. So we can go up and find an example to help you write it correctly. So we'll say if x equals 0, then next state is S1, else next state is S3. And this part of the code will be repeated for every state you have. I'll write when S1, y equals vector 0, 0, 1, 0. If x is 0, next state is S4, else next state is S2, and so on. We'll cover all of the states. So the part from the template originally that I don't need anymore, I can remove and get rid of. So I can remove all of this. And then copy this part, repeat it for every state. Of course, remember to update the output and update the next state based on the input received. Once you're done, you can start compiling and make sure you don't have any errors before running any analysis or running test on ModelSim.